hear me?
Yes, beautifully. Thank you.
Okay, and I hope you also see the slides.
Yes, we do.
Excellent. Okay, yeah. So I am talking about physics at future colliders, and on invisible aspects I'm trying to concentrate. So actually in these three pictures that you see here, you see some of the future colliders that are proposed. So here on the left-hand side, you see the Geneva area where you see Switzerland and France, and this is the LHC. So I'll also talk about the LHC and some prospects from high luminosity LHC. And then there is the FCC. Oh, well, okay, I can't answer that now. This is okay. I hope it doesn't ring again. Okay, and then this is a 100-kilometer collider, as you will, I will talk about that. Another type of collider that's being proposed is the linear collider. The linear colliders. One of them is the ILC in Japan, illustrated here. And then there's also some colliders, circular colliders being proposed in China, although not direct. Okay, I'm really super sorry. I can't. I don't know what to do. So I think the best is that I quickly try to answer. 1 second. Okay, I'm super sorry. All right, so okay, so let me then continue. Okay, so the collider types are on one hand E plus E minus colliders. There's two types. There is linear colliders, ILC and CLIC, and circular colliders, which are called FCCEE or CEPC, and these are often referred to also as Higgs factories. Which is a little bit interesting because actually they produce less Higgs bosons than the LHC, but they have a very clean signature, and so anyway, that's how they're often called. Then we have electron-proton colliders. So they are called either LHEC or FCCEH, and here the point is actually that one parasitically collides the protons that one has in a hadron collider, for instance, as the LHC, also with electrons in a separate collision point. So you still also have PP interactions, but one adds a linear collider, a linear electron collider that collides also with these protons. And then finally, there's of course proton-proton colliders. For instance, in the LHC tunnel, like the high Lumi LHC or high energy LHC, or in a new tunnel like the FCC HH or the so-called SPPC. SPPC is in China, FCC-HH is in Geneva. So as I mentioned already, for E plus E minus colliders, there's these two different types, the circular versus linear ones. And I mean, and they differ quite significantly. What you see in this plot here is the instantaneous luminosity as a function of the center of mass energy. So for instance, you see here FCCEE, which is one of the circular colliders. So you see this gigantic luminosity here at 90 GeV, so at MZ, but then it falls rapidly, and it falls basically with center of mass energy to the fourth power, well, not quite fourth, 3.5 power, due to synchrotron radiation. One has to continue to add energy to get any to add actually luminosity to add current to in fact even sustain this luminosity. So it falls rapidly, the luminosity, and basically is not sustainable anymore beyond say 400 GeV. At this point, you see that you achieve higher luminosity values with the linear colliders. I mean, not quite here yet, but then for linear colliders, the luminosity actually increases with energy as you get better focusing. So the advantage really of the circular collider is that they provide higher luminosity at low energy. You see this also actually for the Higgs physics program. This is the relevant energy point here at 250 GeV, or well, it's not the only relevant energy point, but it is the one where you get access via the H production, where a large fraction of the Higgs boson is carried out. And you see that the circular colliders generally have somewhat higher luminosity than the linear colliders. And the fact that you get very high luminosity or at low energies means that you also have a very strong program for electroweak physics and for also flavor physics, so as a B factory or even tau factory. Linear colliders provide less luminosity at low energy, but on the bright side, they are extendable to higher energies where at some point you cannot have a circular collider because you lose basically all the energy in one turn, and then it becomes, of course, not sustainable. Now, all of them are considered to be quite mature. I might want to show you a plot which is somewhat new, at least to me, relatively new, which is a plot that shows the ratio of the integrated luminosity per energy. So this is motivated by cost, because of course energy costs money. So this is energy now in terawatt hours, but it's also motivated in these days by, of course, the climate crisis, that also there one wants to save energy, right? So you see here also a comparison of these various colliders in that metric. This is so integrated luminosity per energy. And you see also here different behaviors, these ones falling, muon collider, for instance, rising as you go to higher energies. Then the further future is that there's more R&D projects. So these are not quite ready really for prime time. So the muon collider already showed on the previous plot, which collides muons, and I have a bit on that, very little compared to the others, is slightly less material. And then another very interesting development is plasma wake field accelerators, where one can achieve potentially very high gradients, so that one can have accelerators to be much, much shorter and actually also more energy efficient. But there's still a lot of R&D being done in order to make sure one can get high quality beams in the first place, and also accelerating positrons is highly non-trivial. In terms of the schedule, so this is sort of the a view which I took from this paper here. So in red, you see basically the preparatory phase, then in purple, you see construction, and in green, you see operational times, and you see that in terms of, so this is purely technical driven, so not funding driven, because of course all of them cost money. So you see that in principle construction for these Higgs factories could start in 4 to 5 years for some of these cases. For a hadron collider, we're talking about construction starting in 2035 or later. And then for muon collider or plasma colliders, another 5 to 10 years later, potentially. But of course, all of this depends on R&D. So I don't want to go into all the R&D that's necessary. It's also not really my expertise, but you can ask me if you like. Okay, so let's then come to what we want to do at these colliders. And I think one of the exciting things to do at these colliders is indeed looking for invisible things. So there's basically 3 ways that we look for invisibles at collider at present, I would say, or at least 3. So these 3 I want to focus on. One is the so-called monojet or monophoton type signature, where one basically looks for nothing plus something invisible. Something visible, sorry. So one looks for something invisible, which means for us experimentally missing energy or missing transverse energy, but one looking only for nothing is not very, it doesn't work very well, in particular at Hadron Collider. So we need to have something to, for instance, trigger at a Hadron Collider, and here we use a photon or a jet that is basically balanced by missing energy. Another thing is we can look for processes of Higgs production, but where the Higgs decays invisibly. So this is, for instance, Z Higgs production, where we tag the Z boson via its leptonic decay, and then the Higgs decays to nothing, and that it can do that, well, if these hypothetical particles exist, and if kinematically it's allowed, meaning that the Higgs mass is at least twice the mass of these masses of these chi's. And we can look also for more complete theories, if you like, where, for instance, and one famous one is supersymmetry, where there's which predicts many particles that are potentially at the TeV scale or even hundreds of GeV scale, that via cascade decays can decay, and at the end, so in supersymmetry, for instance, the lightest supersymmetric particle is an excellent candidate for dark matter and would indeed be invisible in our detector. So again, we're looking for missing transverse energy plus a bunch of other visible particles. So let me start with the Higgs. The Higgs is, well, so a huge progress has been made since the discovery of the Higgs boson. I'm just illustrating here with 2 plots, well, 4 plots, if you like. So the top row shows the diphoton mass and 4 lepton mass at the time of the discovery in 2012. And the exact same plots are now shown at the bottom with the full data set that we had from run 2. And you see this huge increase in statistics. Yeah, so of course we've used that to learn a lot about the Higgs boson. And the way that for the Higgs boson, the framework that is often used to quantify what is learned is the so-called kappa framework, which parameterizes how the Higgs boson couples to various particles. So in principle, well, so at the LHC, the Higgs measurements depend on both the production of the Higgs boson and the decay of the Higgs boson. So for instance, you can have PP goes to ZH, the Z decays to leptons, and the Higgs goes to fermions. And so you're on one hand, depending on the coupling of the Higgs boson to the Z in the production, and on the other hand, on the coupling of the Higgs boson to whatever this fermion is in the decay. And in the standard model, these couplings are precisely known, and they're actually denoted here, where V is here the VEV, 246 GeV. Now, the only uncertainties that are actually arise from the uncertainties on the mass values, and the masses are rather well known, so that these uncertainties are generally rather small. Now, in order for the interpretation, what is done is simply that one adds an ad hoc scalar modifier, which has a value of 1 for the standard model. So one just multiplies these with 1. But for new physics, they can have non-1 values, basically. So the way the cross-section times branching ratio is basically given then by the cross-section of the standard model times the width of the standard model divided times the branching ratio to the standard model fermions, divided by the standard model total width. And these kappa I and kappa F are these modifiers that are, well, in the standard model they are 1, but in new physics theories they might have a different value. And one can also use this framework to quantify branching ratios into non-known particles. So, for instance, invisible or untagged. And I'll talk a bit about that later. So this is the status. So these are the kappa measurements that have been made by Atlas here in one view and CMS in another view here. So this is a typical plot. These are a bit overwhelming often, but you have all these kappas for the various fermions and bosons, and then these are these branching ratio to invisible and undetected particles. So generally, so a lot of them have been measured, but you see that the uncertainties here are at the level of 10 to 20% typically, yeah. Right, and you see this here also. So what is very nice is recently this result on the muons also that has recently come out. If you then compare what we can do in the future, you see this here. So basically, these are again these kappa values that we know at the moment from the LHC, and in yellow I put what 10% means. So you get just to guide the eye. And in green, you can see what we expect with the high luminosity LHC. So it's basically, I mean, a factor of 5 in many cases, I mean, of the order compared to what we know now, sometimes even more. Or you see it in a different view here. So here 10% is this whole bar. And again, this shows the high luminosity LHC, and it is for many cases below 2%, then some cases below 4%, and only the very rare muon and Z gamma decays will still have a larger uncertainty, but even those are below 5 to 10%. I also should note that this will actually be limited by theory as far as is understood right now, so by theoretical aspects of the uncertainty rather than the statistical or experimental. So, but this of course depends on some assumptions, and well, okay, it already assumes a reduction compared to what we have now, but I'm still hoping that the theorists might do better than what's projected here. Now, if you want to look at all colliders, unfortunately, the plots always become rather complicated. So this now shows, again, for all these kappa values that I just mentioned, so just to guide, let's just discuss one particular example. So let's just actually take kappa Z, which is down here. So it shows the projection for kappa Z, and the different colors show the different colliders, and you can look at it later at your leisure. The light gray is the high luminosity LHC projection with 1.2%. And then you see the various other colliders. So for instance, the plus E minus colliders, they manage to get a 0.3% typically on this. So generally the Higgs factor is achieved about a factor of 2 to 10. And FCCHH dramatically improves further, in particular in rare decays. You see, for instance, for the muon, that actually compared to the high luminosity LHC, the plus E minus colliders do not improve much because the rate is so rare that actually they don't, they have very few events. So they are statistically inferior to the LHC, but the FCCHH dramatically improves. So let me, but however, this is an Invisibles conference, so I want to focus on the invisible and untagged. Actually, I just saw that I'm already at 10 minutes, so maybe I will skip this one. So the direct search for the invisible Higgs decays is really going to make huge progress. So the best channel actually at the LHC is the following one, where you have vector boson fusion to a Higgs, and then the Higgs decays invisibly. And the key observable is these two forward jets. These are high energetic forward jets with a large invariant mass. And this is a plot here from the dijet invariant mass distribution, the data compared to all the backgrounds. You see the data is in excellent agreement actually with the background. And on the bottom, you see this even better in the ratio. Basically, the data scatter around 1. If there was a Higgs boson with a branching ratio of 13% to invisible particles, we would have observed this red line. And that red line is actually excluded by these data at 95% confidence level. This is now just only this one analysis. The full combination of the run 2 data is still outstanding, hasn't been done yet. But if we use this, we can actually translate this. We can try to see, well, what does this mean now in terms of, for instance, comparing it with the direct detection experiments, and this one can translate in given, so that one can compare. Of course, this only works if it's actually kinematically allowed, meaning that MH is at least twice as high as the mass of the dark matter particle. But then you can look at this WIMP nucleon cross-section as a function of the mass of the WIMP. And so you see here, for instance, the xenon 1-ton result, just for your orientation. And then here, this red and the blue shows how you translate basically from the branching ratio limit of the Higgs into this under the assumption that it's a scalar or a Majorana particle. And so you see this cutoff is at basically half the Higgs mass, and then you know, you get pretty good constraints. So ideally, of course, if I could wish anything, I would love it to be sort of in this region, because then we could see it both at the LHC and in direct detection, and I think we would learn most physics if we could see it both ways. But obviously, it's not up to me to wish anything. The future prospects are quite bright here. So at the moment, as I said, we have an sensitivity of the order of 10%. With high luminosity LHC, we'll push this down to 2.6% with a direct search. And then if in the plus and minus colliders, you can get down to 0.3%. So another order of magnitude compared to high Lumi LHC. And with FCCHH, yet another order of magnitude, going to 0.03%, 0.025%, which is actually below the standard model, which comes from the Higgs decaying to 2 Z bosons and both decaying to neutrinos. Yeah, so that's, and then in this plot, which I already just showed you at the moment, what I just showed you was here at 10 to minus 46 in the cross section, and then you could probe all the way down to 10 to minus 49 or something. Similar size, a similar order of magnitude as Darwin, for instance. So the other, what I want to talk about is direct searches for new physics via SUSY and monojet. So let me start with the monojet. I already explained the signature. We're basically looking for something plus nothing. And the key observable here is missing transverse energy. This shows just one example. Again, the data compared to several theoretical models, and you see compared to the standard model expectation plus theoretical models, which have a somewhat harder ET miss spectrum. But the data do not show any preference for a harder spectrum, and they have a very good agreement with the background hypothesis. So this is then often interpreted in sort of simplified models where rather than just having a blob, we actually assume there is a mediator, like a mu Z type boson or something, and then we can actually interpret these data in the plane of the mass of this invisible particle and the mass of this mediator. But we always have to assume something on the coupling. So how the mediator couples to quarks and how the mediator couples to chims. So one has to be that, I'm just saying that because then often one sees plots like these, where again, this is put into the this spin independent dark matter nucleon cross section plot. But here one has to really look at the fine print. So this assumes, for instance, coupling values of 1 for both the dark matter particle and the standard model particle for the mediator. If you choose 0.1 or 0.01, you get significantly worse limits here. Yeah, so one has to be very careful here. But it's just to illustrate also here the future colliders are probing really deep. I mean, compared to high luminosity LHC with FCC, you would gain another 3 to 4 orders of magnitude, and you gain in mass reach because, of course, you can produce heavier mediators, and so therefore also you can have heavier dark matter candidates. Okay, and then the other thing is supersymmetry, which is a very well motivated theory because it can solve or at least reduce the fine-tuning problem of these large corrections. It also has a very natural candidate for dark matter. And I will focus on that here because we're talking about invisible things. It also enables unification of gauge forces at the cut scale, and maybe more, something that's also become even more interesting recently is that it also can provide an explanation for the G-2 anomaly. So the supersymmetric particles, well, there's many of them. So basically for each standard model particle, there's a supersymmetric one. What I want to focus on here is the electroweak Kino sector, it's often called. So basically that the photon, the Z and the W partners, they mix to these charginos and neutralinos. And depending on how, and the lightest of the neutralinos is the dark matter candidate. And depending on how they mix, we call them Wino, Higgsino, or Bino. I don't have time to go into too much detail on that, but let me just say that in for instance, the Wino scenario, you can actually explain the dark matter density in the universe by a single particle, assume if the WINO has a mass of 2.7 TeV. For the Higgs ZENO, it's at 1.1 TeV. What does that shows is that actually in this very simple scenario, you do actually expect it to be heavy. You expect it to be multiple TeV. So you actually need a high energy collider if you want to see that. So we look often for these charginos and neutralinos. These are complex analyses. I just want to show here the present constraints, for instance, at the left. So the green, the blue, and the orange show different analyses. But here, this shows the mass of the neutralino. You see that this plot here, well, the lightest neutralino, it stops at 350 GeV. And this is the mass of the second neutralino, which is assumed to be the same as the chargino, which goes out to 800 GeV. And this area is this little blue thing here in the future constraints. So here, basically at the moment, in such scenarios, we don't say anything for particles, say above 300 GeV, but here we would probe much further, I mean, up to 1.5 TeV in this particular scenario in this neutralino 1, and here up to 3 TeV in the chargino mass. And one can look at it basically in terms of this thermal abundance. So in this simplified case, you see here the mass of the neutralino at 2.7 TeV in the pure WINO case. And you see that with the FCCHH, you will actually be able to probe that directly. And with other colliders, you somewhat short of that. And the Higgs ZENO case, you could also already probe, for instance, with CLIC. Okay, so these are more plots. These are from the muon collider. This is also, maybe I'm running out of time, but maybe let me just say that the muon collider, these are these blue lines here at 3 and 10 TeV, also is actually in general rather competitive in the physics reach compared to FCCHH. Okay, so let me conclude. So future physics at colliders is really a vast topic. I could only give you a small glimpse at the opportunities, and I tried to, well, what the opportunities are that a future collider presents to shed light on the invisible stuff. There are really excellent prospects for producing and understanding dark matter in several different ways. There's, of course, many other exciting topics of future prospects, for instance, the electroweak phase transition via Higgs production, or also the flavor and the electroweak physics programs. So you wonder now, so this picture on the right, so this shows Hamburg on in its normal state, which is a cloudy sky, and it had that sky a week ago when I was thinking about this talk, and incidentally was also the birthday of Bob Dylan, and many of you probably know how many times must a man look up before he can see the sky, which Bob Dylan sings in his anti-war song Blowing in the Wind. So I was wondering, we need a new collider to remove the clouds so that we can then see the invisible.
All right, okay, very good. Thank you very much for this very nice talk. And again, I applaud like everybody else. And I see a raised hand, and this time is a raised hand from Alvaro. I see a raised hand, but I don't see a head. So hopefully we can hear him.
Right?
I can hear
you, yes. But we don't see you.
Yeah, I have a comment and a question.
Yes?
The comment is that if you pronounce WINO instead of WINO, you miss the point of the name as well as the hopes of finding something. You may or may not understand that. Anyway, the question is, are experiments that are done at the LHC, but are not the main 4 collider experiments, such as Phaser, do they have a hope of providing information on the issues that you have discussed?
Well, so I mean, these cases that I discussed directly, I don't think so, but there are, I mean, phaser, for instance, it looks for axion-like particles, among other things. And axion-like particles, of course, are also related. I mean, so I think it probes them in the range of hundreds of MeV, so not in the range that, you know, the strong CP problem axion would be found, but still it's axion-like particles. So I would say, yes, not directly the aspects that I discussed of the Collider program, but of course, in general, to invisibles, it has some relevance.
So it's also, you also have phaser nu, no, but that is not a priori invisible, having neutrinos. But I was going to ask something similar, like what is the interface of what you presented? Maybe you did present it, and as I'm organizing, I didn't follow everything. If so, I apologize. But the interface with displaced vertex, Methuselah program, etc. You see, I like very much your comparison of the direct with the mono signal searches. So in this perspective, how do you see the ensemble?
Yeah, I mean, it's true, of course, that, well, so I didn't present Methuselah, or, I mean, I didn't present, yes, I mean, okay, I presented really what's seen by the mainstream detectors, where basically, I mean, well, in one case, there's the missing ET, right? So that you just see it disappearing. Now, of course, it is true that it can have a lifetime of that is still macroscopic, but not on the, well, but not on the scale of the detector rather than on the scale of the universe. So yes. I mean, but yes. But I didn't present. I mean, I don't know how to do in half an hour. It's very difficult. Yeah. I mean, one thing I should say that some of the, so for instance, these searches here are with disappearing tracks. So there's a large number of analyses now, and also actually the ones here for in the muon collider case. So there you have, it's very degenerate, the masses, and so you actually, I mean, so I mean, yeah, so they're there's kind of displaced analyses, but not in the sense of Methuselah.
Fine.
Yeah, I mean, Methuselah phaser, and of course there's the whole, but this is often discussed in the context of the Beyond Collider program, right? That one has.
Sure, don't. Was just. Okay, thank you very much. Concha?
Yeah, I think we lost Concha.
Lost Concha, so she lost the connection, maybe. Okay, so if there is no more question now, you can ask questions of Beate through the Slack channel. And maybe thank you very much again. And we go to the next while Concha reconnects. So thanks a lot. And we have the pleasure of having Anson Hook to make us think of what is the theoretical perspective. Please, Anson, go ahead.
Yeah, thanks for having me. Yeah, so today what I wanted to do is sort of go back to a sort of an old topic, which is sort of the naturalness motivations for BSM physics, and actually try to explain why I think this is actually a field right now that is actually moving forward and making progress. And rather than sort of telling the philosophy behind it, I want to actually sort of give experimental evidence that sort of theorists are making progress with sort of these naturalness ideas. Naturalness is sort of an amusing thing, because if you talk to any two physicists, they will have different definitions of what naturalness is. And so for the purpose of this talk, all I really want to do is say that this is not the definition of everyone, but just say naturalness is the idea of using dimensional analysis to predict a new scale in the problem.
Yes.
Sometimes this is the mass of a new particle. This is usually what people will want to say, but it's not always. And the reason why we sort of like naturalness is because theory is only useful in that it predicts something to see at experiment. And naturalness is a prediction about where you should see something. And the reason why we believe dimensional analysis, at least, is because experimental evidence indicates that dimensional analysis always works. For some reason or another, if you know the correct physics of the problems, you use dimensional analysis, the coefficient is always order 1. We don't know why, it just is. Just sort of like Occam's razor, which is, it just works for some reason we don't know. And to me, this is the reason why I like physics and not math, is because math, you'll get huge numbers appearing out of nowhere, but this, for some reason, never happens in physics. So in physics, you can guess the answer, whereas in math, you very often cannot. So people like to give a few examples. So for me, since it's dimensional analysis, the simplest example is the one you learn like as soon as you start undergraduate, or not even undergraduate, high school physics, where you just say, if I take a ball and I drop it, at some time I hear something. And so I say, I have a time, and knowing the acceleration due to gravity, I can guess the distance scale to new physics, or where the floor is, basically. Other examples people like to give, for example, are a lot more using classical physics to guess quantum physics. So where you can say that, well, the electromagnetic energy is an energy, and if you have an electron at rest, you would say the typical energy scale is the mass of the particle. And so comparing these two, you get sort of the electromagnetic energy with the rest mass, you get a distance scale where you would say something probably happens here. We don't know what. It turns out what actually happens is quantum mechanics appear and just changes all of the equations. This wasn't actually used to anticipate something like quantum mechanics, but it could have been. The second example people like to give is the charged pion, neutral pion mass difference, where essentially some people sometimes phrase it in terms of divergences, but divergences, these diagrams are just a way to enforce dimensional analysis and the correct spurion analysis. So spurions are just a more complicated version of dimensional analysis. And it could have been used to sort of anticipate the rho meson. Again, it wasn't. But sort of the final example people like to talk about is the charm quark, where it really was a prediction. They really did predict the charm quark mass to be less than, they were pretty conservative in there because they didn't trust their order 1 numbers. And so they had said 10 GeV. But just by looking at the sort of k on, k long, k short sort of mass differences. However, there's actually one more example that I want to talk about of naturalness, which actually sort of points in a different direction, which is, again, a real prediction. So in 1922, Fermi actually predicted the existence of Schwinger pair production, or stimulated Schwinger pair production in his case. And so what he did was he just said, in a magnetic field, particles go in circles, right? You shoot it and it goes in circles. And using dimensional analysis or just using E&M, you can calculate the frequency of the photon being emitted by the electron going in a circle. And he had said, well, it'd be really weird if the photon being emitted had energy larger than the total energy of the electron going in the circle. And remember, this is not a hard and fast rule because classical E&M is actually a sick theory. It has negative energy and everything. So there was no real reason to say that something must happen here. But he said it probably did. And so he predicted that there's a field value. So an energy, not an energy scale, but a field value where something new has to happen. He didn't know what it was because positrons had not been discovered back then. In fact, they hadn't even been proposed. And so he didn't know what would happen, but it turns out what happens is Schwinger pair production, or in this case, a stimulated version of Schwinger pair production. That's actually, astrophysicists will tell us that this process has been observed in neutron stars. So, okay, so this is sort of the idea of naturalness. Now, the elephant in the room that whenever anyone talks about naturalness is the idea of the Higgs boson. And so you can take these previous arguments I told you about of just dimensional analysis, and you predict that something has to happen at the 500 GeV or the TeV scale. Now, the question is, what does that scale mean? Because, right, dimensional analysis just gave you this number. It doesn't say what that number corresponds to. And the answer is, well, it corresponds to anything that has units of GeV. And what people have then said was, well, let's look at examples and see what this 500 GeV scale might correspond to. And traditionally, what it corresponds to are new particles, right? So basically, ideas such as SUSY are what defined this problem to some extent, where they said the particle in supersymmetry, the particles that exist at the 500 GeV scale are the stops, the sort of top partners, so colored scalars. Then eventually people sort of studied more complicated theories such as extra dimensions, little Higgs, and they discovered that the particles could also be, the top partners could also be fermions. They don't need to be scalars. And so we had said, well, at 500 GeV, there should be colored particles. We don't know if they're scalars or fermions. And then finally, neutral naturalness came around, where they discovered that this 500 GeV physics doesn't even need to be sort of colored. So it just had some particle at the 500 GeV scale or before it. So given this, you can say, well, okay, the expectation is that this 500 GeV scale that we identified with dimensional analysis is new particles. And so you can ask, well, what's going on? Like, we haven't seen, other than the Higgs, any new particles. Of course, one possibility is whatever this 500 GeV physics is, it's just well hidden from the LHC, right? It's LHC phobic for some reason. However, as a theorist, I think the more interesting question is to ask, well, if there's nothing there, we must be missing something important, right? Because dimensional analysis always works, and it gives the wrong answer if you don't know all the physics in the problem, right? If you don't know about...
There is a, sorry to interrupt, we have a raised hand in the middle of the talk. It's the first time that this happened. Okay. So I am just going to interrupt you for a second and say if Alvaro has something intelligent to say.
Not intelligent, but it's a question.
Okay, good.
The question is, in your previous transparency, are these people pictured there some particular theorists?
No, this is Fiddler in the Roof when they're singing the famous song.
If I were a rich man. Okay, so yeah. It goes together. Any other question? No? All right, thank you. So you can go on.
Yeah, this is just Fiddler in the Roof when they're singing about tradition. Yeah. And so, yeah, so the question is just, what is it that we might be missing? And it turns out that even before the LHC turned on, people sort of had already developed sort of a two-step program to sort of quit your naturalness addiction. And so the idea behind this approach that people started to take was basically that if different parts of the universe have different Higgs values, this is sort of the step one, is you just write down some theory for where the Higgs mass is different in different parts of the universe. The famous version of doing this is something like the multiverse, where they just have a huge number of vacua and you brute force your way towards having a vacua with a small VEV. Or you could try to do something a little bit more tricky with scanning the Higgs mass. And the second step is just invent a reason why we live in the very non-generic place, which has a small Higgs VEV. Right? This is basically the two-step program people invented to try to get around the necessity of having 500 GeV particles. And there are a lot of famous examples of this. Sort of Anthropics is probably the one that sort of started the whole program, which is just saying that we could not exist anywhere else except for where the Higgs VEV is small. And so that must be the answer. The Higgs VEV is small because we exist. More recently, people have sort of taken a more historical approach where they have said there's a historical reason why we're sort of evolving towards this point where the VEV is much smaller than lambda. I'll talk about it a little bit more later. And the last one is sort of dealing with the measure a bit more. So you'll notice every single one of these problems, every single way, if you take this two-step plan, you have to deal with the measure to some extent. And the measure is unfortunately something about quantum gravity that we don't know. And so you can either try to ignore it as much as possible, or you can just embrace it and try to do something directly with the measure itself. And yeah, it's been a whole list of people doing this. I'm just giving some representative sort of citations here. However, to me, looking at this, you notice something very odd about the whole situation, which is if you look at the solutions to the sort of naturalness Higgs problem, you'll notice that almost all of them are solutions that have never been seen in nature before, right? Supersymmetry has never been seen before. Sort of little Higgs has never been seen before. Anthropics and the measure have never been a solution to the naturalness problem before. And in fact, there are only two approaches really in what I listed, which are old solutions. Sort of composite Higgs, compositeness is what we see all the time in naturalness problems and condensed matter systems. Historical, we have also seen, because you can just walk into any experimentalist's lab and you'll likely find something very fine-tuned like a superconductor or something. And it's obviously not like a naturalness problem. It's because there is some historical reason why there is this fine-tuned object in the lab. And so to me, what we should really be doing is not necessarily inventing new solutions, but taking old solutions and applying them to the Higgs boson, right? So what we should do is just do that. And so what I wanted to really talk about today was just two examples of taking old solution to naturalness problems and applying them to the Higgs boson, and sort of how you actually see that this changes how we might think of the problem. So the first example is I want to talk about how basically in classical mechanics, basically the most common solution to naturalness problems. And so to do this, I'm going to tell you guys about the carbon dioxide CP problem. In the carbon dioxide, it's a plus charged object with two minus charged objects. It's a composite object. And so you can use dimensional analysis to predict what is the dipole moment, right? Dipole moments are charge times distance. So you take the average charge of the carbon dioxide or the carbon particle, you take the distance scale, which you can measure between the carbon and the oxygen, and you say the dipole moment should be something of order this number here. And the carbon dioxide CP problem is the fact that the measured dipole moment is 0. It's not some generic configuration like this. It is 0. And the reason for this, in fact, it's a solution that doesn't even have a name because it's so obvious, is that if you take carbon dioxide and you bend it, it relaxes itself to 0, right? The angle relaxes itself to 0. And so this is essentially how all solutions to naturalness problems work in classical mechanics. It's actually very rare this occurs in quantum mechanics, but in classical mechanics, it is by far the most common solution, which is just if you have something that happens to be very small, maybe it's small because of a dynamical relaxation mechanism. And so it doesn't really have a name, but you'll notice that if you replace carbon dioxide with up quarks and down quarks, you have literally rediscovered the axion solution to the strong CP problem. This is literally the reason why everyone believes in the axion is literally because it is taking what's true for carbon dioxide and applying it to the neutron, right? So because of this, I'm going to just take this approach and call it the axion approach to these problems, even though, like I said, it's so obvious in classical mechanics, people didn't even bother giving it a name. It was just what happened. And so what happens if you try to take this approach and apply it to the Higgs boson? In other words, if you take the Higgs potential, just written here, and you just make the Higgs mass something that changes as a field, what happens? Just make it like an axion. And the answer is, well, it doesn't quite work, but it really almost does. It's surprising how close it is to working. Because if you'll notice, if the Higgs mass is positive, then the VEV is 0 and the potential is 0. So in other words, for all positive Higgs masses, V is 0. And as soon as the Higgs mass is negative, the Higgs condenses and you get some negative energy vacua. And you'll notice two things. One is, unlike the axion, in this case, Higgs mass equals 0 is a maximum, not a minimum. So you're off by a minus sign. And the other thing you'll notice is that 0 is special. This is the hardest thing for any solution to naturalness problems, is making 0 special. And you'll notice 0 is special because it's right on the very edge between being flat and going down. It's like right, thank you, right before sort of rolling off. And so you can see that in order to make the axion approach to the Higgs work, you just need to do two things. Whoops. the first thing you have to do is to flip the sign of the potential, right? You have to take this maximum and turn it into a minimum. And so you have to do that. You have to flip it upside down. And the second is, this thing is completely flat. So everything here is a minimum now. And so you have to tilt it ever so slightly to push you to the very edge where 0 is special. And you can see if you tilt it a tiny, tiny little bit, the Higgs mass goes very small and negative. And so you can see this axion approach to naturalness problems can be solved if you only do two things: flip a minus sign and then tilt the potential. And so this is basically all you have to do to make the axion approach to the Higgs sort of electroweak naturalness works, which is one, you have to scan the Higgs mass. So basically introduce something like an axion that changes the Higgs mass. Two, you have to flip the sign of the potential, which is a non-trivial thing to do. And the final thing you have to do is tilt the potential, which it turns out that the first two things are hard enough that usually you accidentally tilt the potential anyways. So 3 is really, really easy. So in some sense, the only real hard thing here is trying to flip the sign of the potential. And it's not really relevant here. So I'm not going to go into the details of how you actually do this, but it turns out to be possible in a 3 Higgs doublet model, or basically an n Higgs doublet model with n greater than 2. So it's sort of, there's a proof of principle already that you can actually already do this. And the nice thing about this sort of axion approach is that you don't even really need to write down the full model to know what the sort of phenomenological implications are, like how you would look for this, right? You basically look for it the same way you look for an axion, except for a scalar particle instead of a pseudoscalar. So if F is small or if it's heavy, you look for it at the LHC or beam dump experiments by like rare meson decay, rare Higgs decays, etc. And the other interesting thing is if F is large enough, sort of close to the Planck scale, this thing actually starts mediating a fifth force, and we have constraints on fifth forces much, much stronger than gravity, or they have to be much, much weaker than gravity. And so F cannot be too large, unlike the case of the axion. So you're actually dealing with sort of a bounded window to look for these guys. And of course, if you also look at this, you'll notice that this is essentially a scalar mixing with a Higgs. And so this has been studied to death. People have just looked at this coupling, well, maybe not with the sign, but they've looked at the Taylor series of this equation very often. Okay, so this was sort of the first thing I wanted to tell you guys about, or sort of discuss, which is just the axion approach to these problems. The second example is, I told you the example of Fermi predicting Schwinger pair production for a reason, right? Because there is an example where naturalness predicted field values of new physics, right? Where the electric field had to be large enough. And so we're applying naturalness to the Higgs too. What if it's possible, field values also have units of GeV, you notice. What if it's possible that this 500 GeV scale is not the mass scale of new physics, but the field value of new physics? Just like how Fermi what Fermi got when he predicted Schwinger pair production. And so it turns out, at least in a toy model, so we don't really have a version that applies to the Higgs boson itself yet, but at least for a toy model, you can show that quartic couplings have this feature, where naturalness could have actually predicted the field value of new physics and not the mass scale of new physics. Since I'm a little short on time, I'm going to sort of flip through the math a little quickly, but it's actually so simple that if you sort of sit down by yourself for a little bit, you can actually work through it and see what's going on. Because the example which has this is just the axion without the coupling to the gluon. So an axion that doesn't solve the strong CP problem is an example which has this feature. So in other words, usually you have some pseudo Goldstone boson, which sort of spontaneous comes about from the breaking of a U1. Sometimes they call this U1PQ. And then there's some higher dimensional operators that break this symmetry. Usually when you're talking about the axion, you require these higher dimensional operators to be like dimension 15 or something. So like n of order greater than 10. And I'm just going to sketch out very briefly, so it's okay if you don't follow the math. But all right, thank you. So the idea is first you integrate out the radial mode. I'm just taking order 1 numbers everywhere. So the mass of the radial mode is of order f, the VEV. Because you have here a phi to the n, giving you your potential, you have a cosine n phi over f. The coefficient doesn't really matter. So what you can do is take this cosine, Taylor series it, and get a mass and a quartic coupling, and ask, okay, now people have probably heard this all the time when talking about the Higgs boson. Due to the quartic coupling, there's a scale of new physics that's around 1.3 TeV. And so you can apply that exact same argument here, guess mass over square root of the quartic coupling, and you see you identify the scale f over n. In other words, you don't identify the scale, which is the mass of the radial node. You get something that, as you take n large, you get parametrically off the correct mass scale of new physics. However, you'll notice what naturalness has given you is not the mass scale of new physics, but the field value of new physics. Because you'll notice, if I go in field space of order f over n, I see the full cosine potential. My idea of treating everything as just a phi to the fourth theory is wrong if I move out in field space of order f over n. And so you'll see that what naturalness has given you, sort of dimensional analysis has given you, is really the field value where new physics occurs. And so in the case, and I am not doing it here, but you can actually extend this to sort of non-abelian theories like the Higgs. And so if people actually say that, like, oh, the quartic coupling requires new particles at 1.3 TeV, you actually can say you have an explicit counterexample to this claim. In this case, it's actually the field value. So sort of very briefly, the phenomenology of this sort of approach is you sort of look for either higher dimensional operators, right? To see this higher cosine, higher terms, you have to look for higher dimensional operators. So something like a Smeth type approach, or you can actually try to push the scalar distance f over n, which requires high density or high intensity environments. Okay, so it turns out that for Yukawa couplings, you can actually do what I just said, but break it even more badly. I don't really have time, but hopefully sometime this year the paper will come out, but who knows? But yeah, so for Yukawa couplings, you can actually do something very similar. In fact, Yukawa couplings, you have even more options. You can use things, let's say, like discrete shift symmetries, which will give even sort of higher powers of scaling as opposed to the normal n squared is proportional to Yukawa squared type thing. I think on Thursday, Pablo will be talking about at least an application of these sort of ideas to the axion. And so sort of keep tuned for that sort of stuff. But since I'm basically out of time, let's sort of conclude. So dimensional analysis, or sort of its application, naturalness, works, so we have to take it seriously, right? It's just like Occam's razor. For some reason we don't know, it works, so we have to take it seriously. If you apply it to the Higgs boson, it says TeV scale. And traditionally, this is where the mass of new particles is. However, people have been sort of trying to get around this for a while using either multiverse plus anthropics and historical. And what I've been talking about today was basically saying, well, there's actually a new trend, right? Which is just taking old solutions to naturalness problems and porting them over to the Higgs. So this started with sort of relaxion type stuff with the historical approaches, but now there are also these sort of axion approaches, which I sort of mentioned, which is literally just a standard classical approach. I had to put axions in quotes because it didn't even have a name. And the last thing I sort of mentioned was just example from that Fermi gave us, which was that sometimes dimensional analysis gives you the field value, not the mass scale. And so hopefully I've sort of convinced you that sort of naturalness is not really a dying field or anything like this. It's actually changing and sort of gave experimental evidence that it's sort of progressing and evolving. All right, thank you.
Thank you very much. All right, okay, so well, we have a lot of questions here. All right, so let's just start. Let's go back to the first one, which Alvaro is back. Alvaro, can you, I unmute you?
Yes, I am
Yes.
unmuted. How about the dimensional analysis estimates of the value of the cosmological constant?
Yeah, so I would say there, it's harder than the Higgs. So sort of for me, I'm using the Higgs as a starting point because those arguments are essentially the same, or not the same, but similar to the Higgs. And so the hope is that if I can understand the Higgs boson a lot more, like in a lot more detail, then maybe I'll be able to take some of those stories to move it on to the CC. But you'll also notice the one thing I didn't mention was gauge bosons. I talked about Yukawa couplings and quartic couplings. And the reason why is I don't know what to do with gauge bosons because gauge invariance is actually really, really strong. And so I don't quite know how to break those arguments yet. And I'd say if I could break the gauge quadratic divergence, whatever arguments, then I would have a starting point to maybe attack the CC, which is also very gauge sort of like. And so I'd say right now I don't have any comments. I don't want to claim what I can't give yet. So.
Okay, I'll ask the question again in the future.
All right, very good. So another question from Pablo. Pablo?
Hi, hi.
Yes,
Thanks for the
yes.
nice talk. So I was wondering, so you were commenting that now in this kind of solutions, instead of having a new particle like at a given scale, what we have is a new field range, right? And this is associated with the self-interactions of this particle, right? Because we start to probe the region in which it is no longer the quadratic. So how could we test it? Is this self-interactions the promising way, or what could we do?
Yeah, so at least in the case of the quartic interaction, I can say explicitly that it's essentially higher dimensional operators involving only the Higgs boson. So the non-abelian version of this is basically cosine n square root of h1 squared, h2 squared, h3 squared, h4 squared. And you can sort of Taylor series this and start looking for higher dimensional operators involving the Higgs boson. The Yukawa version is actually similar things where higher dimensional operators involving the top quark and the Higgs boson. I don't know what happens for the case of the gauge bosons yet. But without in sort of nailing all the details, so part of the reason why I'm excited about all this is I can't really fully answer your question because the models have not been fully fleshed out yet. At this point, we're still saying, just from the theory point of view, can we say that these arguments were incorrect in sort of how they might be going? And so we're still at the stage of saying, sort of guessing how it might be applied to the standard model itself. So I'd say it's likely this is how it would work. It's just higher dimensional operators involving the Higgs and the Higgs couplings. So like sine Higgs times TT bar type. And then Taylor series that to get h to the h cubed TT bar type interactions. Or h squared.
Very good. Okay, so one last question. Albert Zhu. Hello.
Hello. Oh, hello.
Yes. Yes.
Oh, hello. Yeah, this is a very interesting perspective. It reminded me of a talk I saw from someone from Durham, whom I can't remember, and he had this idea of Higgs explosion. And his claim was that if you consider Feynman diagrams where there are many Higgs, you get some enhancement for some reason I can't remember. And this seems very similar to your idea of a very intense field values, bringing new physics and of course Schwinger production. So do you know about Higgs explosion and whether have you investigated in the context of your work regarding naturalness?
Yeah, so it's not the same thing, but it's in some sense similar to Higgs explosion. So Higgs explosion was just the idea of you just have high energy and suddenly produce many particles. Here, so basically it's the loss of perturbation theory. In this case, everything, because some coefficient here is small, we actually have perturbative control of the theory the entire way through. So you can actually just explicitly just prove without having to do any complicated semi-classical type things. You just perturbation theory. But what it is
But you have operators of infinite order. Sorry, but you have operators of infinite order.
In this case, a cosine potential does, but that's only because you're writing it in some sense like the wrong way, quote unquote. If you do a field redefinition of a cosine potential, you can see, for example, in the UV theory, it's just phi to some power. And you're just taking, because you're taking an angular field, it looks like it's infinitely high dimensional operators. But when you go to the UV completion, it's just not. For example, if you took n equals 4, it's even renormalizable. So it's just
Alright.
the weirdness of taking a 2D plane and working in circular coordinates. And it's just that if you don't know that you're working in circular coordinates, then the way you do it is by higher dimensional operators, higher and higher and higher and higher, higher. But as soon as you start seeing the full cosine, you're like, wait, I'm using the wrong coordinate system. Instead of r theta, I should be using xy. And then everything makes sense and is renormalizable. And yeah.
Okay, very good. I mean, there are other questions, but I think we have to make the break now because otherwise the whole session becomes very late. We are going to have a break.
There is
and,
the Slack. There is the Slack rule for the Slack
Okay.
room for Maxime and the others. So please continue the questions there to Hook, and we will all read the answers because this is very interesting.
Yeah, but I'm sorry. I've been told I have to get a break now, and we will reconvene everybody at 5 sharp, please. Okay, so, and I am okay. So I think with this we'll stop.
Thank you very much for such an inspiring talk. Thanks.
Yes, thank you.